Please, Jasmina.
Thank you. Thank you once again for inviting me and giving me the opportunity to give a talk on this nice seminar. So just a second. Can you see my screen?
Now, yes.
Okay, but I just want to enlarge it a little bit. Okay, so this second part of my talks is about, as Professor Djordjevich say, backward stochastic differential equations with interaction, and it is a continuation on what I was saying about last week. So this is a joint work with Professor Andre, and also a continuation about topics which he mentioned on this seminar. Before I go to main problem, I will give some preliminaries and recall on results on the forward case for these equations with interactions. So let RD be a usual notation for main phase space. We have a sequence on independent Wiener processes on complete probability space. Mu0 will be probability measure on this phase space, and stochastic differential equation with interaction of general form, which was introduced by Professor Djordjev in 2002, has following form. So it has the usual drift with the state-dependent process, this measure mu t and time t, and diffusion is given as a sum of functions bk, which are again fully dependent of time, measure, and state process. This equation has initial condition, which is denoted with U from RD, and mu t is actually given as a decomposition, so mu0 with respect to inverse of process x in time t. Mu t is actually an image of an initial measure mu0 under the mapping x from RD to RD. Actually, this value of process x of ut in some moment t after initial time is a solution, as I call it, a state process of this equation, which is a trajectory of particle which starts from point u in initial moment and contains actually mu t informations from interactions with other particles in some later moment time t. So for some estimates for this type of equation, we will need additional notations. So with this calligraphy M, we will denote the space of probability measures on Borel set B in a complete separable metric space X rho. Space S will be the set of probability measures on X square, which has mu and mi as the marginal projections. So Wasserstein distance of order 0, introduced by Dudley in 1989, is actually given as an infimum of all those measures from C over this double integral. And this distance, together with space M, is a complete separable metric space. In accordance to this, we have also Wasserstein distance of order n between two measures given by this equality. So expression is similar, but with the power n actually replaced with the ratio in previous case. And again, this Wasserstein distance of order n together with the space mn now is a complete separable metric space. We will need both of these definitions in all the estimates for this topic. So a non-random equation of the motion of interaction system for particles is given in following ways. So now we don't have the diffusion. All the coefficients from the sum in the diffusion part are 0. And the drift part is of particular form. So it is given as the integral of some bounded and continuous function f with respect to measure mu. In a special case, when the initial measure mu0 is discrete and given as a sum of probabilities and delta uk's, where all probabilities are strictly positive, so it would have sense. And to UN are different elements from RD. When initial measure is discrete, then also that measure mu t, which is actually the image of mu0 under the mapping X, is given also as a sum, but now we have these deltas with respect to value of state process X. The general equation with interaction degenerates actually to this equation of following form. It has now a drift, which is given as a sum of probabilities and functions f, which are dependent of x in ut and x in ukt, with again initial conditions x u0 for every 0 from Rd. In particular case, for k going from 1 to n, in x, we will, notation is used, x key t is actually x which starts from uk in some point t. These are so-called heavy particles. Heavy particles for these conditions, initial conditions uk. So then previous equation has a simple form, simpler form. Now the drift, the function f is dependent only of interaction between these heavy particles. So actually the flow of this system is that it can describe only the pairwise interaction between these particles and not all the interactions. But this is overcome by generalizing the drift coefficient. And actually drift coefficient A can be defined as a more complex function f, which contains actually all the interaction between all the particles. And it's given in this form. If we denote this with the f tilde, then we have like function SD with interaction, which can describe all the interactions between these heavy particles, not only pairwise interactions. So existence and uniqueness of this kind of equation is also proved by Professor Djordjevich, and definition of its solution is given in this green box. The statement is that the solution of Cauchy problem exists, and it is actually the process X, if for every t greater or equal to 0, restriction on any interval 0 to t is measurable with respect to this product, and for every ut, every initial condition, and every time t, integral form of this equation holds. In same work, he gave the conditions under this exist. So for any continuous functions a and b with respect to all parameters, if in addition a and b satisfied some kind of Lipschitz condition with respect to Wasserstein distance of order 0, given here, then there exists a unique solution of stochastic differential equation with interaction of a general form. So this was all like a motivation for us to revert this theory in, to adapt, not revert, in a case of backward stochastic differential equations. But before I present this, I would just say, would like to say that in general, these kind of equations with interaction describe mass evolution, and they have additional properties to equations which were analyzed until now in stochastic flow theory. And more about this topic in general could be found in reference listed here for some interested listeners. Okay, so backward stochastic differential equations are again defined on complete probability space omega p, where now we will use notation B for Brownian motion. Last week I also introduced spaces M2 on different different actually sets in accordance to the processes which we now need. And the backward stochastic differential equation, shorter BSD with interaction, has this form. So the drift is as in previous case, so it is fully dependent of time, measure mu t, and the process y, which is state process again. The diffusion coefficient is a little bit simpler, but it can be overcome. But for the beginning, we observed only this diffusion coefficient, which has process z. Let me remind you from last week, it is a control component of the pair of the solution for BSD. Now this equation has a final condition. So value of state process in a final capital moment t is value u from RD, and mu t is defined with respect to final measure mu t. So now it is completely opposite definition, and this small mu t is an image of an final measure mu t under the mapping of state process y.
Jasmina, excuse me, and mu t is deterministic, mu capital T.
Mu t, now, yes, in our settings it will be, but we hope that it can be overcome.
Okay, thank you. Because you see, yt is measurable, yt small is measurable with respect to ft.
Yes.
And when you consider image measure, they may be a problem. So that's why I asked about, is it deterministic or not?
I agree. Yes, this is in a connection with the final condition, and I hope it could be generalized, but for now, yes. Okay, this small mu t contains information about the particles, which finishes now in final point u. And in previous moments, they contain information. Actually, the small mu t contains information with the interaction of this particular point with other particles. So we will need the assumption A1, which actually gives the statement that F is measurable in this way. And the definition of the unique solution for BSD with interaction is actually the adaptness of the definition for general BSD. So pair of processes YZ from product M2 M2, which we previously introduced, with the final measure mu t and every value u from RD, such that state process in final condition has value u, is a solution of BSD with interaction if the equation is satisfied and the solution is unique. If for any two solutions which satisfy equation, we have that those two equalities hold. So it is in accordance with the general definition of the solution for BSD. We will observe particular case of function f, which is drift coefficient, as it was done in a forward case. So we suppose that f can be expressed as an integral of some function h and measure mu t. So in the case for discrete measures, if we have discrete final measure, so given in a similarly as in forward case as a sum of probabilities and delta UKs, so probabilities are positive and UKs are from RT, then our measure mu t is given in the following way. So we have now delta of state process in some moment t. Then BSD with interaction for heavy particles. So when we have that values of final condition for state process u, R UKs, have simpler form. So we have that drift is given as a sum of interaction between the pairwise interaction between the particles under the function h, and the diffusion coefficient has only control process of the solution of part of the solution for those heavy particles. So to prove the existence and uniqueness for this discrete type of BSD with interaction for heavy particles, we need Lipschitz condition for function h, which is under the integral of the drift, and it is given with the assumption A2. So under assumptions A1 and A2, the first one is for the measurability and the second one is for this Lipschitz condition. There exists a unique solution for a discrete measure and heavy particles in BSDE framework. So the proof is split in two parts for the uniqueness. If we suppose that we have two solutions which satisfy equation, then subtract the state processes, take square and expectation. We have that, sorry, this inequality holds with respect to some generic constants C1 and C2, because we applied Lipschitz condition and we have that all those members are the same. So we have n same members in the first member on the right side. So if we sum all those equations from 1 to capital N, we have the more generalized inequality. And if we use, because this sum is involved in all of the members, if we use notation that this is sum AT, then previous inequality reduces to this one, which is a simple one. And by direct application of Grunwald-Bellman lemma, we have that first, this is 0 for every k from 1 to n. And let me go back to previous. Then we have directly from the definition of equation. Okay, I want just to show you once again that inequality for the control processes will also hold. So by the definition of uniqueness, we have that unique solution exists. For the existence, as we are in, we observe heavy particle case, so we have that final conditions are as we noted them, UKs. And we start now with iterative assumptions. So we have final condition, but we go back and what we will do for 0 step, we have that y0 is 0, but y is ze satisfy this equation, where now, as by the assumption, drift is completely familiar. And the only thing which is unknown is actually the solution of this simple BSD, which is of the form that drift coefficient is only dependent of time. And actually, we don't even have this G function, it is 0, but I here stated the complete form of the BSD, which is not dependent of the solution in drift, and it only depends of control process in the diffusion. It is from, as I gave like the steps of generalizing the BSD in general form. This is like the first equation which was observed. And solution of this equation, unique one, exists. So by this, we can conclude that we have unique solution of our iterative step. So we further prove that it converges. So similarly as in the proof of the uniqueness, taking expectation of the difference of the square of the solutions, for 2 iterative step, I and I plus 1, we have this inequality is satisfied. So similarly as in its uniqueness, we have on the left side expectation of the square of the difference, but on the right side we have sum of all kind of those expectations under the integral. So we will use the same idea and sum all of those equations from k goes from 1 to n for all those heavy particles. So we will, what we obtain by this, that we have on the left and on the right hand side, same sums which we want to estimate. So from this directly we can conclude, if we denote by A, I and BI, similarly as before, that differential equation has simpler form And if we integrated it, it follows directly that A goes to 0, which is actually a convergence of our state sequence, as we could say. And in the similar way, not in the similar, but in the same way, because we had the both sums on the left side of the inequality, we can conclude that this control sequence converges. So actually we prove the existence of the solution for BSD with interaction with a discrete measure. So our goal is furthermore to generalize this case, not only for heavy particles, but for particles which have final value in any point RD. So we still have a discrete final measure, but we now have any final value U. So this drift is described through function H, which now contains interactions between heavy particles and particles which ends in any point from phase space RD. Theorem 2 states the existence and uniqueness of this kind of equation under, again, the conditions for function H, assumptions A1 and A2. So let me remind you, this is just Lipschitz condition and measurability condition. This proof goes straightforward from the existing theory for BSD, because this equation is actually let us look it once again. So it has drift, which is dependent from the state process of any particle, which ends in any final moment, and these heavy particles. So it can be fitted in the general form, even though the drift is even simpler. It doesn't depend on control process. And the diffusion is even simpler because this function G in our case is 0. So it is a subcase of this general theory. So as the solution of this equation exists, we then have the result of existence and uniqueness of the solution of our BSD with interaction with a discrete measure and any final condition. We need this for the approximation case for more general BSD with interaction. So furthermore, now not only that we generalized final condition, but we also generalized the drift. So now the drift is given by general function H dependent of any state process and measure mu t. Any measure mu t, and our idea is to generalize, to approximate the final measure via the discrete one, because we already give the full description of the BSD under the discrete measure.
Jasmina, may I ask one more question? Do you have some regularity of y with respect to parameter u? For example, continuous version of y with respect to u?
We didn't assume, and as I believe we didn't use it anywhere, actually.
Let me comment. Of course, in order to have some approximation, we need the estimation on the regularity of y with respect to spatial parameter. And we have such estimations. Yeah.
But this is, you mean, okay, in that sense, we have like auxiliary, I will show you just in next slide, but I thought that like an assumption, we don't need it, we prove it actually.
No, this is not an assumption. Of course, we did it in the proof, yeah.
Sorry, I didn't understand the nature of the question, but it's actually given here.
Yes.
Okay, so I asked about this statement.
Yes, but I thought that you asked like an assumption, and we actually prove it later. Yes, this is, as we call it, some kind of stability with respect to parameter u. So let me just give the notation. So if we have two drifts for two equations, actually, BSD with the generalized drift, Then we show that solutions satisfy some kind of stability with respect to final conditions, regularity, as Professor Pilipenko emphasized, and with respect to Wasserstein distance of order 2. So proof is using the same steps as in previous results. So if we subtract those two equations, we have integral form of new BSD actually with interaction. And if we apply to formula on the difference of the square, we have this expression on the right-hand side. And now we will apply expectation, lose the member with respect to Brownian motion, use the Lipschitz condition, and again applying, because we have appropriate form for application of Gromov-Bellman lemma, we have the desirable result for the state process, stability result for the state process. So we will have this plus integral with respect to Wasserstein distance in accordance to some other generic constant C. And then going back to this inequality, we can use the same estimation for the control processes. So actually this stability, as we call it, or regularity, is for both processes from the solution with respect to final conditions. Sorry, I just wanted to see, but this is just weightings. Okay. So main theorem is theorem 3, which in the same time gives the approximation of any final measure mu t. We add this discrete measures mu t n in the sense of Wasserstein distance of order 2. And as a consequence of these approximations, we have that if un and zn are pair of solutions of BSD with discrete measure and final measures mu t n, and uz is a pair of solution of BSD with respect to any final measure and any final condition, then we have that this convergences, these approximations hold, which is actually equivalent with the statement that we have a unique pair of unique solution, unique pair of processes which satisfy BSD with interaction. So by the definition of Wasserstein distance, we have that expectation of the square of Wasserstein distance of order 0 of order 2 can be approximated from above with this expectation. And if we add and subtract the UVT here and use elementary inequality, we have two members in sum on the right-hand side of this inequality. Further on, as this is not dependent on U, it can be simplified. And we used for the second member Fubini theorem just to replace.
I'm sorry, Jasmina, could you please recall what is kappa? What is measure kappa?
Is the set of measures which have U and mu and ni as marginal projections.
Mu and mu, okay, thank you.
Yes, so that's why we passed here to mu, because we don't have any dependence here on another measure actually. This is for the first member. For the second member, we still have a full dependence, U and V. So we are still having kappa here. And we will estimate separately both of those members on the right-hand side. So for both of them, we will use this stability result, but in first member, this one, where we pass to measure mu, we don't have dependence of, a final condition is actually the same. And from that regularity inequality or stability, we have that first member on the right-hand side vanishes. So we only have this Wasserstein distance of order 0 on the right-hand side. For the second member, actually, as we have that, we already we have similar, but sorry. Yes, but now we lose this part for Warshaustein distance, and we only have the difference of final conditions, because now here we have the different final conditions are involved. So we use the same inequality, but with a different result. If we replace it, so we have for the first estimate, for the first member, only Warshaustein distance part, and for the second one, only the final condition part. By the definition, this is again Warshaustein distance of order 2. So we have that this is this reduces to given inequality. So this is again appropriate for applying Grunwald-Bevel lemma for Warshaustein distance of order 2. So we have that approximation for Warshaustein distance when n goes to infinity, as by the assumption in final moment they're close. We concluded that also in any time t before capital T, we have approximations of approximation of measure mu t by discrete measures mu t n. So this is our main fact which we'll use in the proof for the existence of the and uniqueness for the solution. Actually, now we can, I will go back, we can again use this previous theorem for the stability / regularity, this one, as we proved that now when measures are close in the final moment t, there will be close, the approximation will hold in any time t. This will go to 0 when n goes to infinity. And by the assumption we have that conditions, the final conditions are the same for the approximation sequence and our BSD which we observe. So this will also be 0. So we have that sequences of approximation converges. So actually we have the solution of BSD with interaction with respect to general measure mu. So two main facts which are used is this auxiliary lemma for regularity, stability, and the convergence of measures mu t in any time t. This would be all. I would just like to give the list of references which we use. So some of them I already mentioned. These are just some regarding to BSD. These are professor's book for equations with interaction in forward case and general theory. Some other papers. We use this book for inequalities. Then distance and another results from stochastic flow theory, which I already mentioned from Filipenko and Lagunova. And these two references I already gave last week just for BSD theory. Yes. So this would be all. Thank you for your attention and questions for now. Are there more questions or remarks maybe?
I would like to say that your lemma 2 is a very good result, because this lemma implies that y is continuous with respect to parameter t, with respect to parameter u.
Yes.
Just apply, say, Kolmogorov type, Kolmogorov theorem. And if you have, by the way, if you have measurable modification of u with respect to u and t, only in this case you can push your measure.
Even for, yes, yes.
And it seems to me that you maybe have even locally uniform convergence yn to y in probability, because you have compactness in the space of continuous mappings, continuous in U.
Mm-hmm.
And you have convergence in L2, you have uniform estimates, so probably you have uniform convergence. Even so, maybe uniform in U, not expectation, not only in mean square, but in uniform.
Yes, yes. But here I also think that we can even obtain higher power estimates with respect. So it can be also, but Professor Djordjevich didn't want to go further. He said this is enough. So, but it can be, yes, also estimated.
Well, for continuity in one-dimensional case, if U is one-dimensional parameter, this is enough. For multi-dimensional cases, probably you need a little bit more.
Yes, yes. But for now, we stopped here because idea is to use this for the control problem, which we are discussing now, not for properties.
So you want to associate these backward stochastic differential equations with some control problems for usual measure processes with interaction.
Yes, this is actually the main idea, but when we set up the problem, we see that we need first all of those results in order to continue with this control setup. So this is the motivation. The motivation is control, but this is just the results on the way to the main problem, actually, yes.
And your final condition is just identity map. Your final condition, why U T capital is U.
Yes, yes, yes.
And is it possible to, but when you study backward stochastic differential equations, ordinary backward stochastic, the final condition may be random variable.
Yes, from L2, yes.
Is it possible to write your equation maybe for random y of T capital, but deterministic measure mu T capital?
I also had the same remark to Professor Djordjevich to generalize it even more. But as I mentioned, he said, for now, it is enough to have this, and later on we will see. So hopefully we can extend it. Yes, and I promise that I will also, I will come back to your remark, but just to say one more thing, it would be nice if we would have more general equation, as in forward case, to have more general coefficient here. And this would actually not be a problem if we have here, in addition, function g, which depends only on state process. Then we can, because myself, I had the results in a BSD framework, to have like a substitution between this so-called non-homogeneous, which would have in addition function g with respect to state process, and to connect this homogeneous, which only has control process. It could be done by simple substitution. So this equation can be generalized, even though the first result is only for the control process. So as I stated, I would like us to have a general result when the final condition can be even random, not only from RD, and to have more generalized diffusion. But for now, we only proved these results, but hopefully we will generalize them in these two directions. So just to have like complete BSD with interaction. We'll see.
Okay, thank you very much. Maybe some other questions? I just want to recall that we decided to publish surveys related to our lectures in our journal Theory of Stochastic Processes. So I hope that Jasmina also will do this, maybe in much more general context and with motivation which we discussed today. Thank you again. Our next speaker will be Alexey Rudenko. And let me remind you that we have some lectures which we unfortunately skipped in March, but I think that we will continue our readings in the June, and Katerina Glinina will send everybody a new scheduler. So we will continue our readings in the June. Again to everybody, and see you next week. Bye.
Thank you. Bye.
Thank you for interesting talk. Goodbye. Have a good day.
Thank you. Bye.
We also